Good afternoon to all participants. Sir, I am Dr. M.V. Samsarao, Assistant Professor, Department of Physics, Bapatla Engineering Career, sir. Sir, we are organizing this FDP. Sir, a hearty welcome to a 3-day National Faculty Development Program, FDP, on quantum technologies, emerging trends in physics and computation, QTETPC 2026, in view of National Science Day celebrations. We are all aware that Sir C.V. Raman was an Indian physicist who won the Nobel Prize in Physics for discovering the Raman effect. This groundbreaking finding, discovered in 1928, provided evidence for the quantum nature of light and led to Raman spectroscopy, a vital material analysis tool. In view of this occasion, our nation celebrates National Science Day on 28 February every year. In the part of these celebrations, we are organizing this FDP. This is a specialized program initiative designed to bridge the gap between theoretical physics and modern computational applications. Quantum computing is a rapidly emerging technology that uses quantum mechanics to solve complex problems in simulation, optimization, and cryptography far faster than classical computers. This program aims to equip educators and researchers with the skills to teach and conduct research in the rapidly evolving quantum landscape. Quantum computing represents a paradigm shift from deterministic classical bits to probabilistic qubits, enabling exponential speeds for specific complex problems. As of early 2026, the field is transitioning from theoretical milestones to quantum utility, where quantum systems provide reliable solutions for problems beyond the reach to brute force classical simulation. Sir, now I request our senior faculty member, Dr. C. Anjaneyalu Garu, to compare the program. Sir, Anjaneyalu sir, please take your session, sir.
Thank you, sir.
Sir.
Thank you, sir. Good afternoon to respected dignitaries, esteemed resource persons, and enthusiastic participants. I am Dr. C.H. Anjaneyalu, coordinator and of the program QTETPC 2026, and it is my absolute honor to welcome you to this 3-day journey of intellectual growth. So education is lighting of a fire, it's not a filling of a pail. So during this 3-day program, we will explore this fire through our 3-day FTP QTETPC 2026 as a cornerstone of Industry 4.0. Quantum computing redefines the computational limits by leveraging the superposition, entanglement, interference, etc. It processes the information quickly, qualitatively, and quantitatively. Q for 4, 3 Qs. Okay. So to formally commence this FTP, I first invite my colleague, Mr. L. Nageswara, to say a few words about the life sketch of Sir C.V. Raman. Welcome, Eleanor sir. Please take the proceeding. Eleanor sir.
Yes, sir. Okay, sir.
Welcome, sir.
Yes. Click.
Good afternoon to one and all. Myself, L. Nageswara, working as an assistant professor in Department of Physics, Bapatla Engineering College, Bapatla. And I am very glad to present the biography of Sir C.V. Raman on the occasion of this 3-day FDP on QTETPC. Sir Chandrasekhara Venkata Raman, popularly known as Sir C.V. Raman, was a great Indian physicist who was born on November 7, 1888 in Tiruchirappalli, Tamil Nadu, India. He was one of the most brilliant scientists of India and made important contribution to the field of physics, especially in the study of light. Raman completed his education at a Presidency College in Chennai, where he showed exceptional talent in science from young age. while working in Kolkata at the Indian Association for the Cultivation of Science, Raman conducted experiments on the scattering of light. In 1928, he discovered that when light passes through a transparent substance, a small portion of the light changes its wavelength. This discovery was later named the Raman effect. His discovery proved that light interacts with molecules and changes energy, which helped scientists understand the structure of matter. For this remarkable discovery, Sir C.V. Raman was awarded the Nobel Prize in Physics in 1930, making him the first Asian scientist to receive this honor in science. He also received many other awards, including the Bharat India's highest civilian award in 1954. In his Nobel lecture, Raman said, "The essence of science is independent thinking and hard work, not equipment." This message still inspires students worldwide. Sir C.V. Raman served as a professor at the Indian Institute of Science in Bangalore and later founded the Raman Research Institute. He was not only a great scientist, but also an inspiring teacher who encouraged young students to pursue science. Sir C.V. Raman passed away on November 21, 1970 in Bangalore, India. He is remembered as one of India's greatest scientists, and his discovery, the Raman effect, remains very important in modern science. The famous slogan of C.V. Raman is, "Ask the right question, and nature will reveal its secrets." This motto encourages students to be curious and persistent. Thank you, one and all. And now I am hand over the session to Dr. C. Chanjanelu. Sir.
Thank you, sir. Thank you,
Sir, sir.
for your speech about the about Sir C.V. Raman. Excellent. Now I invite Y. Chaitanya sir to share a brief overview of our physics department and its profile. Welcome, Chaitanya sir. Please take the session.
Thank you, sir. Good afternoon, all.
Yeah, good afternoon.
Good afternoon to all. I am Chaitanya, working as Assistant Professor in Department of Physics, Bapatla Engineering College, Bapatla. I am pleased to present our department profile. The Department of Physics was established in 1981 with the objective. So the Department of Physics was established in 1981 with the objective of catering to the academic needs of engineering students. Over the years, the department has expanded its academic programs by introducing MSc Electronics in 1992 and MSc Physics in 2001, thereby significantly strengthening its contribution to postgraduate of qualified and experienced faculty members specializing in core areas such as quantum mechanics, electronics, solid-state physics, and nuclear physics. Currently, 4 faculty members hold PhD degrees from reputed universities, and 3 are pursuing their research, thereby further enhancing the academic and research strength of the department. The department is well equipped with modern laboratory facilities, including the optical laboratory, electronics laboratory, modern physics laboratory, and a dedicated research laboratory. These laboratories are providing students with comprehensive hands-on training and valuable research exposure in various domains of physics. Dr. V. Aruna, HOD, Department of Physics, got a UGC-funded research project in 2017. Under this project, essential research equipment such as 2 muffle furnaces, a digital balance, and a density measurement accessories were procured. These facilities are effectively utilized by MSc Physics students for their project work and research activities, thereby enriching their experimental and analytical skills. Dr. V. Aruna and Dr. C.H. Anjaneyulu sir have been recognized as research guides. Under their supervision, 2 PhD scholars and 4 MPhil scholars have been successfully completed their degrees. At present, 3 PhD research scholars are pursuing their research under their guidance, reflecting the department's strong research mentorship and academic commitment. The department has made significant contributions to research and academic excellence. Faculty members have published nearly 100 research papers in reputed national and international journals. The department also takes pride in the achievement of Dr. A. Ramesh Babu, who serves as reviewer of reputed international journals, bringing academic distinction and recognition to the institution. The college library further supports teaching and research by providing an excellent collection of physics resources, including 1106 titles and 3413 volumes, enriching the rich academic support for both students and faculty. The department is committed to continuous academic growth and is planning to introduce new specializations in emerging areas of physics and to undertake more funded research projects in the future with a vision to become a center of excellence in physics education and research. This is the brief review of our department. Thank you all. Now I hand over the session to Dr. C.H. Anjaneyulu, sir.
Thank you, sir, Chaitanya, sir, for giving excellent explanation about our department. And now it is time to invite our chief guest and beloved principal, sir, Dr. B. Srinivasarao Garu, to address the gathering and share his valuable message. Principal Srinivasarao, sir, please take the session, sir.
Yeah, thank you. Am I audible?
Audible, sir. Audible. You are audible, sir.
Okay, thank you. Thank you. Resource persons for this 3-day FDP on the quantum technologies emerging trends in physics and computations 2026. Dr. R. Shankaran, sir, Professor of Physics, NIT Tirchi. Dr. S. Balakrishnan, sir, Associate Professor, Department of Physics, VIT Vellore. Dr. Muthu Ganeshan, sir, Research Assistant Professor, Department of Physics, SRM, Tamil Nadu. Convener for this 3-day FDP, participants, and my dear friends. So this 3-day FDP on quantum technologies and emerging trends in physics and computation in the view of National Science Day 2026. I welcome you all for this 3-day FDP on quantum technologies and emerging trends in physics and computations. See, the main objective of this FDP is to introduce some core principles of quantum computing, curriculum integration, and research advantages. So definitely this 3-day FDP will help a lot for all the participants. So I once again congratulating my team for conducting this 3-day FDP. So thank you. Thank you.
Thank you, sir. Thank you very much, sir.
Thank you.
So now I invite HOD Department of Physics, Dr. V. Aruna Garu, to give a message about the this FDP. Welcome, madam. Please take the session.
Thank you very much, sir. Good afternoon to all. Myself, Dr. V. Aruna. Myself, Dr. V. Aruna, Head Department of Physics, Bapatla Engineering College. On behalf of the Department of Physics, I extend a warm welcome to everyone to this online National Faculty Development Program, Quantum Technologies, Emerging Trends in Physics and Computation. It gives me an immense pleasure to address you today as Head of the Department of Physics, Bapatla Engineering College. Our department is conducting this FDP as part of the National Science Day celebrations, which are observed every year on 28th February to commemorate the discovery of Raman effect by Sir C.V. Raman in 1928. His groundbreaking work not only earned India its first Nobel Prize in Science in 1930, but also placed our nation firmly on the global scientific map. National Science Day serves as a reminder of the power of curiosity, research, and scientific developments in nation building. At the outset, I considered it my foremost duty to express my heartfelt gratitude to our management for their constant encouragement and support in organizing meaningful academic programs. I also extend my sincere thanks to our esteemed principal, Dr. B. Srinivasa sir, and our former principal, Dr. N. Ramadevi madam, for their valuable guidance, encouragement, and unwavering support in conducting this FDP. The primary objective of this national FDP is to focus on emerging and transformative technology, that is quantum computing. Quantum computing is a revolutionary field that harnesses the fascinating principles of quantum mechanics to solve problems that are beyond the reach of classical computers. Recently, on February 7th, 2026, the Honorable Chief Minister of Andhra Pradesh, Sri N. Chandrababu Naidu, along with the Union Minister, Sri Jitendra Singh, inaugurated the Amaravati Quantum Valley in Amaravati. This ambitious initiative aims to position Andhra Pradesh as a global leader in quantum technologies, with a focus on quantum computing. The first quantum computer under this initiative is expected to be operational by December 2026, marking a significant step toward technological advancement and national development. To briefly explain, quantum computing operates on the principles of superposition and entanglement. Unlike classical computers that uses bits, either 0 or 1, quantum computers use qubits, which can exist as both 0 and 1 simultaneously. This property, known as superposition, allows quantum systems to process vast amounts of information at once. Another fundamental principle is quantum entanglement, where two or more qubits become interconnected in such a way that the state of one instantly influences the state of the other, regardless of distance. These unique properties enable quantum computers to solve highly complex problems in areas such as cryptography, advanced simulations, artificial intelligence, optimization, and many more. Recognizing the importance of this emerging domain, our Department of Physics has taken the initiative to organize this FDP to enhance awareness and deepen understanding of quantum computing among the faculty members. I'm confident that this FDP will be highly beneficial and intellectually enriching for all participants. I'm truly honored to welcome our esteemed resource persons, Dr. R. Sankarnarayan sir, Dr. S. Balakrishnan sir, and Dr. R. Muthuganeshan sir for this FDP. Your expertise will enrich our FDP on emerging trends in physics and computation. I strongly believe that today's all the sessions will broaden our perceptives and enhance our knowledge in this cutting-edge and rapidly evolving field. Before I conclude, I would like to say that our greatest strength lies in our dedicated faculty members. Let us continue to learn, collaborate, and innovate together for the advancement of science and society. Wishing you all a fruitful and successful FDP. Thank you, one and all.
Thank you, madam. Thank you very much for your explanation about the introduction to quantum computing. Now, we are privileged to have Dr. Subramanian Balakrishnan sir with us today, and a pioneer in quantum computation and quantum technology since more than 20 years, and also sir has more than 75 years regard. of high quality publications, both through the Google Scholar also. Dr. Subramanian Balakrishnan led our first session today about the foundations of quantum computation. Now I invited Dr. Ramesh to give a brief introduction about Subramanian Balakrishnan sir, today's resource person. Welcome, Ramesh sir. Please give a brief about the resource person, our today's person.
Thank you, sir. I am Dr. A. Ramesh Babu, working as an assistant professor, Department of Physics, BEC Bapatla. Good evening, all. Welcome you all to 3-day National Faculty Development Program on Quantum Technologies, Emerging Trends in Physics and Computation. It is my privilege to introduce today's resource person, Dr. S. Balakrishnan, sir. Dr. S. Balakrishnan, sir, is an associate professor in the Department of Physics at Vellore Institute of Technology with over a decade of experience in teaching, research, and academic administration. His research focuses on quantum computation, quantum information theory, and quantum game theory. He has published over 50 research papers in reputed SA Index international journals and actively contributes to academic development through research supervision, invited talks, and administrative leadership. Educational qualifications. He got his PhD in physics in May 2012 from the National Institute of Technology, NIT, Tiruchirappalli. His doctoral thesis was titled Non-Local Characterization and Applications of 2-Qubit Gates under the supervision of Dr. R. Sankarnarayanan. His broad area of research is quantum computation and information, academic and administrative contributions. Dr. Balakrishnan has held several administrative roles at VAT. Awards and fellowships. Dr. Balakrishnan received the OSA Student Travel Grant from the Optical Society of America in 2008. He was also awarded the CSIR Senior Research Fellowship for the period 2010 to 2012. Research guidance. Dr. Balakrishnan has successfully guided one PhD scholar with the thesis titled Investigation of 2-Qubit Entangling Operators in Quantum Game Theory, awarded in 2025. Currently, he supervises 6 PhD scholars working in areas such as quantum computation, quantum game theory, and quantum machine learning. He has also guided 18 MSc thesis projects and other academic credentials. He has served as guest editor for a focus collection on quantum game theory in the journal Quantum Information Processing, Springer. He acts as a reviewer for reputed journals, including Scientific Reports, Quantum Information Processing, International Journal of Theoretical Physics, Physica Scripta, APL Quantum, Journal of Physics A, Physica A, Physics Letters A, and Ramana. He has also served as a judge for science exhibitions and as a resource person in various science outreach and training programs. Thank you. Thank you all.
Thank you, Ramesh sir. Excellent explanation about our today's resource person. Now I will now hand over the session to our esteemed resource person, Dr. Subramanian Balakrishnan sir, to take the session. Thank you, sir. Welcome, sir. Please, sir. Please welcome, sir.
Okay, thanks a lot. Can you hear me?
Yeah,
Yes,
it is
sir.
audible,
Yes,
sir. Audible.
Okay,
Audible.
thank you. Thanks a lot.
Audible, sir.
Yes, sir. So it's my pleasure to be here, and I'm really honored to be here. And I must thank all the organizers of Bapatla Engineering College, Bapatla. I would like to thank Principal Sir and HOD Madam and all other colleagues who are involved in organizing this 3-day FDP. And in fact, this is the very right time to train our faculty colleagues, and hence the students can also be trained in the upcoming revolution. And I hope you people must have heard about artificial intelligence. In a very short span of time, a lot of discussion happened. And of course, in the recent time, India also conducted, AI India Summit, which attracted a lot of people across the globe. And in the future, I would say when quantum computation merges with artificial intelligence, we are going to witness yet another revolution. So we should keep up our face and keep learning and try to engage ourselves as well as to the future generation in this domain. And so with this brief note, and before I start, I'm very glad that this event is also being arranged as a part of National Science Day to commemorate the remembrance of beloved scientist Sir C.V. Raman. So before I move on to the session, I would like to share an incident happened in the life of Sir C.V. Raman. So after he receiving Nobel Prize, Sir C.V. Raman was invited to America just to honor him. And so he attended the function held in USA. And, pretty well in foreign culture, after the, meeting, they used to have drinks, right? So one of the scientists from abroad invited to have him some drinks. Okay. Then Raman told him very politely, I allow you to study Raman effect on alcohol, but never I allow alcohol effect on Raman. So that was the reply he made. So it was a very interesting statement, very polite statement made by Sir C.V. Raman. Right. So with this, once again, I thank all the organizers. Let me move on to my session. So I request the help of organizers to let me know whether the screens are visible.
Visible, sir.
Yeah, it is visible, sir.
It is visible, sir.
Right. Thanks a lot. Thank you. Right. So before I start, I want to say a few things. Quantum computation is highly an interdisciplinary subject and multidisciplinary aspects, right? So when you say quantum computation, basically it involves people working from mathematics point of view, physics point of view, computer science point of view, electronics point of view, and electrical engineering point of view. So all these people should come together, then only one can do the breakthrough. In fact, whatever breakthrough we have witnessed so far come from people work together, different background people, namely from physics, mathematics, computer science, electrical and electronics engineering. They come together, they work together, and then we have seen a very great breakthroughs. Okay, so having said that, it is not necessary, one should know everything. For example, computer science background people may not know what is a physics point of view in the domain of quantum computation. Similarly, people working from physics point of view may not aware where it can be applied in the so-called artificial intelligence or computational. Nevertheless, one should know the crossroads where we can meet and where we can distribute our work so that one can see a great application of the subject on the whole. Right. So with this, the very first day of the session, how I planned was something like this. So it has 4 different segments. And that too in the afternoon, I never want to take a very strong subject of quantum mechanics or quantum computation. Rather, I would like to narrate the story of quantum computation. So as I said, quantum computation is nothing but so-called application of quantum mechanics in computation. And hence we have a subject called quantum computation. So in other words, quantum computing, quantum mechanics gets married with classical. You have all the participants. I request you to make a note of it. So let us proceed the session slowly and steadily. You make a note of the questions, and towards the end, probably we can have a question and answer session. Right. So with this brief note, once again, I thank the organizers. Let me move on to the very first segment. And to keep my participants, very active, I always ask questions. So let me start. Right. I hope you can see the very first slide. Can you see the first slide? I'm in the slide showing Galileo Galilei. Can you see slide number 2? Anyone can confirm?
Yes, sir. Yes, sir.
Oh, right. Thank you. Thank you. Right. So I always start the story with this gentleman, Galileo Galilei, who is very known to us. He was the one who invented telescope, which helped us to see the distant object. And of course, Galileo Galilei, though we regard him as a philosopher, the modern day historians treat him as a very first scientist, because Galileo Galilei was the very first person who taught us to look at nature from a scientific point of view. So during his period, all the natural phenomenon are looked at a different point of view, but he was the one who insists us to look at nature from a scientific point of view. In that sense, Galileo Galilei is regarded as a very first scientist. Right. I want to have your attention in the year in which Galileo Galilei passed away. Right. He passed away in the year 1642. The name of the scientist who born in the year 1642. You can make a wild guess. Any guess? He's well known to us. Okay, so he was none other than Sir Isaac Newton. Correct. He was none other than Sir Isaac Newton. Right. Interestingly, he was born in the year 1642 on a Christmas day. Right. And moment we say Newton, we know his contributions, right? When we say Newton, we always talk about, mechanics. So mechanics is the subject which has been individually developed by Newton. Right. So when we say mechanics, it's we know very well first law, second law, and third law. Third law of Newton is very famous. To every action, there is equal and opposite reaction. Right. So if you look at Newton, he had a very miserable life because he lost his father before he come into existence, and he was solely developed by his maternal grandmother. And during his period, he had undergone a pandemic. Right, we had undergone a pandemic due to corona. During Newton's period, there was a pandemic that was due to plague, and so all the institutes shut down, and he came home. And perhaps he started working on the concept of gravity and so on and so forth, right? And then he started working on mechanics and first law, second law, and third law. He published a book, and it is called the Principia. Basically, Newton was very, very timid, never expressed his idea at all, and hence, because of his friends' push and encouragement, he published. And during that work, he realized that the scientific language was not sufficient to express the idea, and hence he took the help of mathematics, and that is nothing but differential calculus. So differential calculus was introduced by Sir Isaac Newton, and that was one interesting aspect. And another thing was Newton also worked on a concept called Armageddon. So Armageddon is nothing but a end of mankind. It basically, Armageddon is a biblical term which tells you that it's a battle between good and bad, and so end of mankind. So according to Newton's calculation, we have something around 2064 would be the end of mankind. It is his calculation, right? So much of work and a very, very important contribution, and perhaps one individual like Newton can contribute this much. Okay, so in the Google Scholar page, you must have seen this statement: "Stand on the shoulders of giant." Basically, these statements are uttered by Sir Isaac Newton. So Newton made a statement about Galileo Galilei. Newton saying that I'm standing on the shoulder of a giant so that I can see a longer distance on the ocean. Right. So he was referring to Galileo Galilei. So Galileo Galilei was a giant in the sense that he was the one who taught us to look at nature from a scientific perspective. In that sense, Newton was very much inspired by Galileo Galilei, and he made this statement. Right. So, okay. So one of the reasons I always say sarcastically, on a very lighter side, why Newton could contribute this much. So Newton contributed, on this concept of mechanics, gravity, right, Armageddon, differential calculus. And he also importantly worked on the concept of what is light. So whether light is made up of particle or a wave, that was the question. And during his period, Newton was saying that, light is made up of particles and it's called corpuscular. So corpuscles are the particles. So according to Newton, light is made up of scientists. Hygiene. He proposed light as a wave. So Newton was saying light is consists of particle, whereas hygiene was saying that light consists of waves. Since Newton was at the power, no one recognized hygiene, not for 1 year or 2 years, merely for 300 years. 300 years, no one recognized wave nature of light. Okay. Right, that was the story. And later, Heinrich Hertz came and performed experiments. Then we started looking at wave nature of light. Okay, so that was the interesting aspect of Sir Isaac Newton. Right, so now traveling to 200 years later, we have this gentleman. His name was James Clerk Maxwell. He famously known as Maxwell's equation. Right. So nearly for 200 years, people thought that electricity and magnetism are two different aspects of matter. Right. So electricity is coming from charges, magnetism coming from magnets, not pole, pole permanent magnet. And they thought that, people thought that there were no connection between these two. But very interestingly, Maxwell found a mistake and he very elegantly fixed it. And then the four basic equations are known as Maxwell's equation. So Maxwell's equations are very significant in all the communication process. So you are hearing my talk because of this communication, satellite communication, because satellite communication do obey Maxwell's equation, and Maxwell's contribution was very profound. And Maxwell was treated as a very first theoretical physicist. Okay, so I want to have your attention on the year in which Maxwell passed away. He passed away in the year 1879. Right. So can you guess the scientist who born in the year 1879? I can show you the picture now. I hope you can find out quite easily. So he was none other than Albert Einstein. He born in the year 1879. So Albert Einstein born in the year 1879. So look at the interesting points then. Galileo Galilei was replaced by Sir Isaac Newton. Maxwell, the very first theoretical physicist, was replaced by another giant in physics, none other than Albert Einstein. Right. So when we say Einstein, we always think of special theory of relativity, general theory of relativity, and all. But interestingly, Albert Einstein got Nobel Prize for his outstanding work on photoelectric effect. So photoelectric effect was a very interesting phenomenon which was realized by Einstein, and he got Nobel Prize for it. The interesting part of the story is that he got Nobel Prize, Albert Einstein got Nobel Prize, exploiting quantum mechanics to explain photoelectric effect, but Einstein did not accept quantum mechanics till his death. So he completely against so-called quantum mechanics. You will understand why. Right. And I also put this, he was also treated as a philosopher. Though Albert Einstein was very well known as a scientist, but I would say he was also an excellent philosopher because very many hard concept, very philosophically he made. So in that sense, I always recognize Einstein as a philosopher. Right. So I narrated the battle between so-called, Newton and hygiene. So Newton proposed particle nature of light, hygiene proposed wave nature of light, and no one recognized hygiene for 300 years, right? So similarly, a similar sort of battle happened between two gentlemen, Albert Einstein and Niels Bohr. And of course, I'm talking about the same Niels Bohr who proposed the so-called atomic model. Right. So here, very interesting aspect, Einstein did not accept quantum mechanics. The reason being quantum mechanics is basically a probabilistic nature. So it's a probabilistic theory. It's not a deterministic theory as like classical physics. So I will explain these two terms as we proceed further. Right. On the other hand, Niels Bohr was a very strong believer in quantum mechanics, and there were a lot of interesting conversation happened between these two. There is an excellent book written by a Nobel laureate called Andrew Whitaker. The title of the book is Einstein, Bohr, and the Quantum Dilemma, from quantum theory to quantum information. It's an excellent book which talks about how two intellectuals, namely Einstein and Bohr, contemplate themselves, deliberate themselves to understand inaccessible microscopic world. So this book just had in Salt Lake Congress meeting and all. So it was a nice book to read on to understand the history. Right. Now, having said that, classical physics, which was developed by Newton, 300-year-old, and people thought that, okay, everything was done in science, right? Because all the macroscopic object simply obeys Newton's first law, second law, and third law. And of course, we also have electromagnetic theory. And so a charged particle can also be explained. So having a well-developed science during the period of late 18th century, why scientists were forced to introduce a new subject called quantum mechanics, right? So in a sense that if we know why classical or where classical mechanics failed, we can understand the origin of quantum mechanics. The very first instance was this structure of an atom. So this was $1 million question at the end of late 18th century. People really asked the question, okay, we have elements, various elements in the periodic table. Okay, fine. What is an atom all about, right? What is the building block of the entire universe? So we have an answer for that. The entire universe is made up of, fundamental elements, namely an atom. So we have something like a wall, and the wall is made up of bricks. So brick is a fundamental building block. So similarly, the entire universe is constructed out of the atom, right? But what is this atom all about? So we try to understand the structure of an atom. So do late 80s, okay, fine, electrons start to move. Yes, okay, fine, electrons start to move. Something like, very blind comparison with the planetary motion, but it should not be the case. We cannot compare the planetary motion with the electron motion. Okay, so what happens here? The electrons, once again, it's a charged particle. So when it revolves, what will happen? It will dissipate energy. So after some time, the kinetic energy becomes zero and velocity becomes zero. The electron becomes stationary. Once electron becomes stationary, it must be attracted by the positively charged proton, which is present inside the nucleus. So electron is supposed to enter into the nucleus. Once again, we never seen an electron inside the nucleus. So the classical idea of explaining an atom bitterly failed. So we don't know how to explain the structure of an atom using classical mechanics. The second instant was hydrogen spectrum. So we know very well hydrogen is a gas. And when you excite the hydrogen by supplying a high voltage, it will go to the excited state. And while you pull it, it comes down. We expect to see something like a continuous spectrum, like a tube light, right? We are getting a tube light from the tube light continuously. But interestingly, the experiments are validated. You cannot really suspect all those observations. You need to check your theory to explain all those observations. So this was a scenario where people forced to introduce a new domain called quantum mechanics. So let us see how it was introduced. So this is the first segment, right? So Samuel, sir, can you confirm the screen? Can you see the electromagnetic spectrum?
Yes, sir.
Yeah, right. Yeah, Newton single-handedly developed a subject called mechanics, also known as Newtonian mechanics. Later, 200 years, we have very first theoretical physics, namely Maxwell. Maxwell was replaced by Albert Einstein. Albert Einstein, we know how contributed in the domain of science, in particular physics. And the question of why scientists were forced to introduce a new subject called quantum physics, because classical physics failed to explain some of the experimental observation. Right. So continue the story. So here you can see the electromagnetic spectrum in terms of wavelength. So the longer wavelength is radio waves, and as you move further and further, you have gamma rays, and correspondingly you can see the figures. So when you say radio wave, it is something like a tall building, and as you go to the gamma ray, very small size of an atom. So size of an atom is something like 10 to the power minus 10 meter, 1 angstrom size, and something like 10 to the power minus 15 meters. And interestingly, the wavelength, frequency, and the color, right? Frequency, wavelength, and color, these are all interrelated. Right. To establish this, let me show you this picture. Right. This is a very famous picture called, Predator, acted by the very famous Hollywood actor, right, Arnold Schwarzenegger. Right. I hope most of you people must have seen this movie. As per this movie, this is an alien which is depicted as a villain. Note that a human we can see in the range something like 400 to 700 nanometer. The entire electromagnetic spectrum, we can see only a small region and it's called visible region, ranging from 400 to 700 nanometers. Right. On the other hand, as per this movie, this alien can see only in the infrared region. Right. When you say infrared region, so through the eyes of alien, it can visualize human something like this. Right. Why it is so? Because human is a warm-blooded animal. It is nothing but a thermal sensor. It's nothing but a thermal sensor. Okay. Right. So it can see only in the thermal in the infrared region. So all the notion of wavelength, frequency, color are interrelated. As a matter of fact, even William Shakespeare used to tell if someone is angry, his eyes become red. Right? It's called a red hot eyes. When we say red hot eyes, it means someone is very angry. Okay, so why I'm narrating all the story? Because frequency, wavelength, color, all these things are interrelated. That is why we need this concept called a black body. Right. So black body is an ideal object which absorbs all the temperature, all the radiation, and it emits all the radiation. So we try to do some experiment. People did that, and you can see the graph over here. So we define a quantity called spectral energy density, which is nothing but total radiation by unit volume and unit frequency. So along x-axis, you have wavelength. Along the y-axis, you have spectral energy density. So you can see that this is developed. Note that it's an experimental observation, nothing to do with the theory. So people perform black body spectrum with the different metals, and they got a graph of this sort. So on the right hand side, you can see the same graph, but once again, the graph is plotted this time with the frequency against the spectral density. That's why there is a reverse feature one can see. Right. So black body spectrum was a very interesting observation. People tried to do with the different metals, and they did, and they got this graph, similar sort of graphs, and they tried to explain why the graph become like this. It increases and decreases. So we try to explain it by means of our theory. So the very first person who come into picture was VN. So VN was the one who tried to explain. He found that as the temperature increases, peak of the curve shift towards lower end. In other words, as the peak reduces, so that the product remains a constant. So the constant value is 2.898 10 to the power minus 3 meter Kelvin. And this is called VN's displacement law. Because why a displacement? Because the peak of the curve shift displaces from one point to another point as the temperature increases. It is interesting to note that even now we are using this formula to calculate the surface temperature of a distant star. So from the color, we can find out what is the wavelength. Once we know the wavelength, peak wavelength, then we can use this formula to calculate the surface temperature of the star. Then you can understand the significance of this expression, PL. Right. Then we have a person called Boltzmann who joined with Stephen, and they come up with a formula. R is nothing but total radiation. So mathematically, the area under this curve is nothing but the total radiation, which is proportional to 4th power of the temperature. Meaning, if the temperature rises from T to 2T, then the total radiation increases to 16 times. Why? Because T to the power 4. Right. And here you must have come across this term, his name, Boltzmann. Boltzmann was an excellent physicist. His contribution was very profound. He lived a very short time. Okay. And he committed suicide in a hotel in Vienna. Right? Not because of love failure, rather he could not solve an equation. So he hanged himself in a hotel. Right? The sad part of the story was the equation what he tried to solve was already solved. That was the sad part of the story. Nevertheless, Boltzmann did a very profound work in statistical physics. Right. Then people come to explain, Wien also tried to explain the graph, and it is something like this. And the other expression is this. This is the most important one. It's called Rayleigh-Jeans formula, wherein hardcore classical physics ideas were implemented to explain the graph. As per the formula, you can see the total radiation is proportional to square of the frequency. So the theory says that as the frequency increases, the total radiation increases to infinity. But what is our experiment says? Experiment tells you as the frequency increases, total radiation increases. But after some time, after reaching a peak, it turns down. So it is a very finite value. It never goes to total radiation, never goes to infinite range, right? So, but hardcore classical physics tells you that the energy goes to infinity. So this was the contradiction, and the scientists really got fed up, and they used the terminology ultraviolet catastrophe. Right. I hope you know the meaning of the word catastrophe. So catastrophe is nothing but complete destruction. It is a complete destruction to classical physics. Why? Because the hardcore classical physics tells you that energy goes to infinity as frequency increases. But your experimental observation tells you that energy never goes to infinity, it is only finite. And why the word ultraviolet? At the ultraviolet region, it goes to infinity as per the theoretical prediction. So scientists really got fed up. They could not know how to explain the concept of black body spectrum. Right. So this was the scenario. Right. At this time, the very first hero of quantum mechanics, his name was Max Planck. So Max Planck entered into picture. He gave a very revolutionary idea. The revolutionary idea was this. Right. So what is the revolutionary idea? The energy and the so-called frequency. So it is the frequency actually. So the energy and frequency are related by this. So what is this equation? Why it is very revolutionary? Energy, we always talk about energy of a particle. We always talk about frequency of a wave. This is the very first expression which connects wave and particle characteristics. Wave and particle characteristic. That is one thing. The second revolutionary idea was whenever light interacts with matter, the energy exchange happens not in a continuous fashion, but in a quantized way. Right. What is quantization? Now you can see. Right. So in the energy levels in the microscopic world, in the atomic system, it's not like a continuous one as we imagine. Rather, it is a kind of a ladder. So it is the first step, it's the second step, third step, like that. It's the first energy level, second energy level, third energy level. So it is the first energy level, second energy level. So it is HF is nothing but fundamental energy, and other things are just integral multiples of it. Integral multiples of it. So this is how the energy levels are being arranged, or one can understand in that way. And whenever the so-called electron jumps from one energy level to the another energy level, it emits so-called photon. So photon, the very interesting term coined by a chemist. And what is photon basically? It's an energy carrier. So whenever light interacts with matter, light gives energy in the form of a photon. So photon is a basic entity. Photon is a basic unit which has the energy. Right. What do you mean by quantized? So here one can think of, when you say quantized, you can imagine a ladder, step 1, step 2, step 3. You don't have anything between two steps. Right. So similarly, in the microscopic world, the energy levels are like that, and it is quantized. So it was complete a revolutionary idea because no one ever thought about it, but Max Planck himself introduced out of kind of frustration. Right. So why it's significant? Because when Max Planck introduced this notion, namely E equal to h nu, and put it in the theory, and he got into the expression, it is called Planck's radiation formula, which very elegantly explained the so-called black body spectrum. So the black body spectrum was very precisely explained by so-called Planck's radiation formula. Why it works? Because of the very fundamental assumption according to Max Planck, E equal to h nu. So photon is an energy carrier. Whenever light interacts with the matter, then energy exchange takes place by transferring the photon. So this was the notion began in introducing so-called quantization. So it's called Planck's quantization formula. In fact, Max Planck himself told, out of frustration only he introduced, and it fit into theory very nicely. Very nicely. So the so-called black body spectrum, the very first hurdle of quantum mechanics or classical mechanics, was very elegantly solved by a new concept called quantization principle, Planck's quantization principle, E equal to h nu. Right. We always say E equal to mc square, right? Einstein introduced a mass energy relation, E equal to mc square. So similarly, this expression, this equation is also so important in science, E equal to h nu. Right. So now, if you look at the equation as such, E equal to h nu, as it is proposed, as I said, E is the energy of a particle, nu is the frequency, and energy always we associate with the particle, nu is the frequency of a wave. This expression connects the so-called wave and particle characteristic. As such, this expression tells you that a wave can behave like a particle. This expression indicates that wave can behave like a particle. And what was the experimental confirmation? The experimental confirmation was given by this gentleman, Arthur Compton, and it is known as Compton effect. So what do you have here? You have actually he took carbon and consists of electron, and Compton allowed X-rays to interact with the electron. So X-rays consist of photon, and photon interact with the electron like a billiard ball collision, and these electrons scattered with the smaller energy, and X-rays scattered with smaller energy. Why it is so? Because part of photon's energy is given to this electron. Not whole energy, but part of the energy is given to this electron. So electron goes like this, and the photon lost some of the energy, moves with longer wavelength, shorter frequency, and hence shorter energy. So Compton effect was an experimental confirmation of particle nature of waves. Right. Having said that, the French physicist Louis de Broglie confirmed the other way around. Right. What is the other way around? If nature allows particle to behave like a wave, then nature should also allow wave should behave like a particle, the converse. Right. So what our friend de Broglie was saying is that whenever a particle is in motion, it exhibits wavy nature. You imagine a particle which is in motion and it exhibits wavy nature. So if that is the case, why we are not able to see wavy nature in the macroscopic world, right? For example, when a bowler throws a ball, the ball never goes in a wavy form, right? It moves in a projectile form, right? Why we are not able to see? Because of the factor sitting on the numerator of this expression. Lambda is the wavelength, h is the Planck's constant, p is the momentum of the particle. So if you take the order of this Planck's constant, it's something around 10 to the power minus 34. Very small number. 10 to the power minus 34. 0.33 zeros, following which we have a significant digit. So such a small number, and for a macroscopic object, that is very insignificant. That is the reason why we never ever realize wave nature at a macroscopic world. But at a microscopic world, the mass of the particle itself is very small. For example, you take mass of an electron, which is of the order of 10 to the power minus 31 kilogram, right? So Planck's constant 10 to the power minus 34 and mass of an electron 10 to the power minus 31. These two are comparable, and hence we start to see the wavy nature at the microscopic world. So in fact, de Broglie used this word, nature loves symmetry. Nature loves symmetry. What do you mean by symmetry here? A particle can behave like a wave, and a wave can also behave like a particle. This is what the symmetry is. So, this is the starting line of a PhD thesis of de Broglie, and he got a Nobel Prize. Right. What was the experimental confirmation? The experimental confirmation came from Davis and Germer, which proves that wave nature of particles. So, especially electrons. So electron, when it is accelerated, it is diffracted by the crystal, nickel crystal, and one can see the de Broglie wavelength. And this is nothing but de Broglie wavelength can be calculated, or matter wave can be determined. And it was a direct experimental confirmation of wave nature of particles. Interestingly, Davison and Germer got Nobel Prize for their experiment, along with a person called G.P. Thompson. So G.P. Thomson also performed this experiment in America. Davison and German performed it in England. And G.P. Thomson was none other than son of J.J. Thomson. J.J. Thomson also a Nobel laureate who proved that electron works as a particle. So father proved electron as a particle, son proved electron as a wave, and both got Nobel Prize. Both father and son got Nobel Prize working on the concept of electron. Right. Moving further, the very profound pillar, very difficult to digest this concept. It's called uncertainty principle. So Werner Heisenberg, so he was saying that there are certain canonical pairs. So there are certain pairs in physics, namely position and momentum, energy and time, angle and angular momentum. These quantities cannot be determined simultaneously. Note that these canonical pairs also exist in classical mechanics, right? There is no doubt about it. But interestingly, these pairs, namely position and momentum of a particle, energy and time of a particle, angle and angular momentum of a particle cannot be measured simultaneously with 100% accuracy, right? So when Heisenberg proposed this idea in front of Albert Einstein, Einstein was really objected. He was saying, marvelous. Nowadays, youngsters have a lot of imagination. And he refused to approve the PhD work of Heisenberg. Okay. And Heisenberg, he was a student of Sommerfeld. And both Sommerfeld and Heisenberg went to Einstein, took some time. And Heisenberg performed a thought experiment. It's called Gedanken experiment. It's a German terminology. Gedanken means imagination, thought experiment. So he come up with a concept called Heisenberg microscope. And he convinced Albert Einstein, and later he got Nobel Prize in front of Albert Einstein for his work on uncertainty principle. Initially, people thought that we cannot measure certain quantities simultaneously because we don't have instrument. We don't have instrument to measure them precisely. Right. When I say this, I always give an analogy with the cricket match. So in cricket, now the technology being used. So we test whether the ball will hit the stump. How we solve it, how we do this, very simple. We know the velocity with which the ball is released by the bowler. We know the trajectory of the ball and we extrapolate. We solve basically Newton's equation. F is equal to ma is being solved because we know the initial position, initial velocity. We can always find out the projectile motion and we can check whether the ball will hit the stump or not. And note that you have two detectors. One is to measure the position, the other one is measure the velocity. So these two quantities can be determined simultaneously with 100% accuracy in the macroscopic world. But in the microscopic world, the scenario was completely different. Why it is different? When you try to see the position of an electron, you disturb it. And the mere attempt of seeing where the electron is disturbs, and hence it acquires a different energy and hence momentum. So moment you try to measure the position, you don't have idea about momentum. Moment you try to measure momentum precisely, you don't know where the electron is. So both the quantities cannot be measured simultaneously with 100% accuracy, and it is called uncertainty principle. Right. Putting all these pictures together, this is the summary of quantum mechanics. Right. So what is the summary? Talks about Planck's quantization principle, which tells you that E equal to h nu. So energy of a particle and the frequency are related. And the converse idea was put forward by de Broglie. It's called matter waves. So what is the symmetry? Why nature loves symmetry? When nature allows wave to behave like a particle, then particle should behave like a wave. That's what we call it as symmetry. Nature loves symmetry. And experimentally, it was confirmed by Compton effect and Davison Germer experiment. And later, Heisenberg come into picture. He gave a very revolutionary idea. It's called uncertainty principle. As a matter of fact, uncertainty principle is due to wave-particle duality. What is wave-particle duality? So it's something like two sides of a coin. At a given time, I can see only one side of a coin, right? So similarly, I can find out either wave nature or particle nature of light. So in fact, you can yourself do a simple experiment in the home, right? For example, you take a light and take a small pencil or pen and you keep a screen, right? When you keep the pen very far away, you don't see the shadow on the screen, right? When you keep the pen closer and closer to the screen, then you see the shadow. Why it is so? Because the light coming out of the source behave like a particle. Particle travels in a straight line and it stopped, and hence you see the shadow. So this wave particle duality, it's very surprising, and because of which we have uncertainty principle. And the experimental confirmation was done, and it is through the experiment called two-slit experiment. A lot of interesting YouTube videos are available to understand that two-slit experiment through simulation. I welcome our participant to see that. Right. This is the most celebrated picture in the history of mankind. So there was a place called Salve in the year 1927. All these people gathered, and why they gathered to discuss about so-called quantum mechanics. It's called quantum mechanics and how mathematically one can frame the subject of quantum physics. Right? We know very well classical physics cannot explain some of the experimental observation, and hence new notions were introduced. What is the mathematical formulation that was decided here? And if you see this picture, all these figures are known to you, right? Starting from Marie Curie, Rutherford, Albert Einstein, Wolfgang Pauli, Schrödinger, all of them were Nobel laureates. It's very hard to see one single photograph where these many Nobel laureates can be found. So this was the picture taken in the year 1927. Right. Now we are in a position to move on to the next domain called, computer science or computers as such. Right. Before that, let me conclude this particular segment by highlighting the quote of Niels Bohr. If quantum mechanics has not profoundly shocked you, you haven't understood it yet. Right. So why it was so surprising? Because of few facts, which we will discuss as we move on to the next segment. Right. So let me move on to the next segment. Okay. So it is an introduction to quantum computation. So formally, I will introduce after introducing so-called computer science. Right. I hope you can see the third segment, classical computation. Sir, can you confirm it, sir?
Yes, sir.
Okay, thank you. Right. So, having seen the history of quantum mechanics, parallelly there was a subject called computation. Right. What is this computation? Computation is nothing but IPO model: input, processing, output. That's it. That is a very simple logic. That is the essence of computation. So you feed a number 2 plus 2. Something happens in this device, so-called a calculator, let us say, and it gives you an output, right? And if you execute the statement hello.xe, then you have a word, hello world. This is the very first statement. And in fact, scientists are looking forward to see a word, hello quantum world. If you have a quantum computer, that would be the very first one people try to look into. Right. So this is the idea of classical computation. And when we say classical computation, we cannot forget the father of theoretical computer science. He was none other than Alan Turing. So Alan Turing, I tell you the story. See, basically all this notion comes from the war field. So First World War and Second World War. So especially in the Second World War, which happened during the period 1939 to 1945. So German government, especially Hitler, they have used an instrument. They have used a very encrypted language. It's called Enigma. So Enigma is a secret way of communicating the instructions across the globe. So Hitler had that power in the sense that he deployed this and he was able to control it. And I would tell that was an instance where people introduced the notion of artificial intelligence. So the notion of artificial intelligence, though it was coined very later, 1958 or 9, the notion was already exist by the government, Germany. Okay, so now that so during that period, war period, what was happened? Alan Turing was a mathematician and an engineer, and he was deployed to encrypt and decrypt the notion of Enigma. So Enigma codes is very difficult to decrypt, and the task was given to Alan Turing, and he started working on it. Then he went to USA to take over his PhD work. So this happened just before the before the World War, and he went to Alonso Church. So from England to USA he went, and he started working with Alonso Church, and he developed a mission, and it's called the Turing mission. So Turing mission, it is something like universal mission. In principle, it can compute anything man can compute. So whatever I can compute, for example, I know how to do addition, subtraction, integration, differentiation through mathematics. I acquire a knowledge I can do. It means I can also feed these knowledge to my machine. It can also do. So my machine can also perform all this task. So that is what it's called. It's called a Church-Turing thesis. The Turing machine can compute any computable function. Anything what you can do mathematically, the machine can also do, but in a different way. What is the way it has to work? It has to work on a tape. It's called infinite. Theoretically, it's called infinite tape, wherein zeros and ones come into picture. You see the bits, binary digit. Bit is nothing but binary. It's an acronym of the word binary digit. Zero and ones come into picture. Right. He started using it. And he proposed a concept of, Church-Turing thesis. And Turing machine is a very primitive so-called computer. So he started using it. So very simple logic was, to decrypt the Enigma code, why a man has to do? A machine can do that, right? It is something like to handle a mission which has artificial intelligence. We develop a mission which also has an artificial intelligence. So these two missions can interact. So that was an idea put forward by Turing, and hence he developed this mission called Turing mission. So understand the notion of introducing so-called a computer was developed to decrypt a mission called Enigma. Okay, it's not a machine, rather it's a cryptographic language. Okay, so interestingly, there was a story about Turing. Turing, after this, he went to after completing PhD, went to England. He worked for the government, and after which, World War got coming to end. He was deployed as a scientist and all. So what happened was, during after few years of the World War, 1935 to 45, then 52, around 52, he was given a task, okay, as a government scientist. He was given a task. He was working, and what happened? His house was burglarized. It means it was theft happened in his home. He gave a complaint, and police came and found him that he was a person involved in characteristic of homosexual behavior. So during that period in England, homosexual attitude is not legal, and hence he was given a punishment. So he was given two options: either he has to undergo a medical treatment or lifelong prison. So when this judgment came, within 3 to 4 days, he found dead in his home. Even it was a mystery how he was dead, whether it was suicide or murder. A lot of interesting stories are there available. If you are interested, you can go and read. But interesting point is UK government very recently come forward and apologize the contribution of Alan Turing. So Alan Turing family was given, kind of pardonized for being a kind of a very wrong treatment to a well-known intellectual, Alan Turing. And now it's a legal term in England. It's called the Turing law. Turing law is nothing to do with science. Turing law, it's a legal term. Someone was given a pardon after their death. It's called the Turing law. Okay, just a piece of message, because there must be many computer scientists among the participants. Right. So coming back to the story of Church-Turing thesis, so the so-called the first Turing machine was developed, and the classical computer was developed because semiconductor technology was also evolved during the period 1930 to 1950. So during this period, 30 years period, many revolution happened. We moved from valve era to semiconductor device, wherein PN junction diode, transistors, and all those things were developed. And we got in a position to develop the very first machine called classical computer. So the classical computer, if you see, it occupies the entire room. This was the size of the very first computer developed, but you know the story now, right? We have so-called, our mobile phone. Our mobile phone, in fact, if you have an Apple phone, it's nothing but a mini computer, right? So the so-called, the size of the computer has reduced very tremendously. And over the years, it has been reduced. And Gordon Moore was a co-founder of Intel. So we know very well, right? Intel Pentium processors, right? So Gordon Moore was a co-founder, and he made a prediction. Interestingly, he made this prediction in the year 1970. It was something like a roadmap of his company called Intel. So he made a prediction. The prediction was, if every 18 months the number of transistors keeps increasing, density of transistor in an IC integrated circuit keeps increasing. If that is the case, what would be the scenario? We will be reaching around these many transistors in the year 2010. Okay, so now the point is, there is no more space to put one more transistor in your integrated circuit. You exhaust all the space, meaning to say you have gone up to the level that you cannot increase the speed of the computer. You cannot decrease the size of the computer. And interesting to see that this graph tells you how the company of Intel produces the processor. Intel 3 processor, 4, 5, 6, 7. Right now we have 11, 12 and all. Okay, right. So Gordon Moore predicted that we cannot decrease the size, we cannot increase the speed of the computer. Right. So that was the scenario. And according to him, by 2020, lost all the space in the integrated circuit. There is no possibility of decreasing the size and increasing the speed of the computer. Right. So now, having known this problem, computer scientists hand over this to the physicist. Why? Because computer scientists come to know that, okay, they exhaust all the space and they cannot work on so-called microscopic world. Why it is so? All your computer, classical computer, obeys macroscopic law, nothing but Newtonian mechanics, right? But as you go further down to the microscopic level, you cannot apply Newtonian mechanics, you cannot apply classical mechanics, you can apply only quantum mechanics. So computer scientists come to the conclusion that they are moving towards microscopic world, as they don't know what is quantum mechanics. So they handed over this problem to the physicists with the hope that physicists understand quantum mechanics in a better way. But ironically, physicists also had a difficulty in understanding quantum mechanics. Right. So given this scenario, the major breakthrough happened through this gentleman from quantum computation point of view. So he was none other than Richard Feynman. He was a Nobel laureate, and he delivered a talk among the computer scientists in Caltech, and in the year 1985. So the essence of the talk was very simple. You see, whatever characteristics we depict, it's not ours, it is our ancestors. See, for example, we always tell to our kids, you look like your grandmother, you look like your uncle, you resemble the characteristic of your maternal grandmother, like that, right? So our kids resemble the characteristic of our ancestors. So we also exhibit the characteristics of our ancestor, meaning, for example, I never know hunting. I don't know how to hunt an animal. But if you keep me and put me in an Amazon forest, saying that all along my life I have to be there in the Amazon forest, slowly I have to start to hunt, right, for my survival. So then the so-called the skill of hunting will come into picture. The information of hunting is already stored in my gene from my ancestor when they were in the cave. So nature is capable of storing huge amount of information in a small physical entity called gene. So gene is a one which has every information about our ancestors. So the characteristics are sometimes suppressive, sometimes dominant. So all the informations are still available. So if nature is capable of storing huge information on a physical entity, why not you try to mimic? Why not you try to do it in the laboratory? So that was the motivation given by Richard Feynman among the scientists. Right. After which the two pathbreak works came. One is from Peter Shor, other one is from Grover's algorithm. Okay, so I will take these two algorithms in the last segment, namely the next segment, because I need to introduce some of the basic terminology. Right. So this is the story of computer science. So I hope you understand. So computer science, how it evolved from Turing, and who developed a machine to attack another machine called Enigma. And we try to understand how this machine works, Turing machine. And because of semiconductor revolution during the period 1930 to 1960, we got into the very first computer, and the computer occupies the entire room. And now, as we go on developing the technology, we have a very small computer in our hand. Right. So now what is the problem? The problem is that as we keep decreasing or increasing the transistor in the IC, we don't have any space at all. Meaning to say, we are moving from macroscopic world to microscopic world. So in the microscopic world, you cannot apply classical physics, you have to apply quantum physics, and hence quantum mechanics get into the picture of computation. Right. So now let us see what is the basic terminology we need to know. Right. The story in the case of quantum computation is very simple. You need to know certain terminology. Let us say, what are they? Quantum states, in short, qubits. Quantum gates, nothing but quantum operators. Physical realization, what are the candidates that are being used now to realize quantum computer, and a concluding remark for this particular segment. Right. So what is qubit? Qubit is nothing but the analog of classical bits. Right. As I said, bit is nothing but a binary digit, 0 and 1. So in another language, we can say on state and off state. On state and off state. What is on state? What is off state? When the voltage is closer to 0 volt, 0, 0.1, 0.2, 0.3, then you say it's a off state. When the voltage is closer to 5 volt or 4.9, 4.8, then you say it's a on state. So on state and off state are given as a binary, zeros and ones, and all our computer read or understand only binary language. Right. So in the case of microscopic world, what we have, what is the analog of it? We have analog, it is called a qubit, and it is a notation, it's called Dirac notation, which I'm not going to discuss in detail. It's completely different topic altogether. Rather, I want to tell you that, so this notation is very important if you really want to understand the subject of quantum computation. Right. So qubit is nothing but quantum bit. So quantum bit, in short, it's called qubit. And what is the analog of it? It's very simple. You have, let's say, nucleus and the first energy level. You know very well, energy levels are discrete or quantized. So the ground state energy, the least energy possessed by the electron, which you call it as get zero. It's a zero state. It's something like off state. But when you supply a voltage or a frequency of suitable light, then what will happen? This electron goes to the next energy level, excited energy state. And this is nothing but on state. It's nothing but state. It's state 1. So it is called on state. This is called off state. Okay. So it's a two-level system which can be thought of a qubit. So if you ask me the question, sir, only we can think of atomic system to realize a qubit? No. We do have other systems, so something like photon. Photon has a concept of polarization. So left polarization is 0 state and right polarization is 1 state. So like that, we have other physical proposals as we will see as we proceed further. Right. So quantum state, what is the speciality of quantum state? Right. The speciality of quantum state is nothing but superposition of allowed state. See, get 0 is nothing but on state, off state. Get 1 is nothing but on state. The linear combination is also an allowed state. Right. I give you an analogy so that you can understand. So if you have a switch in your room, you can see it has only two information, right? It can be either on state or off state. You don't have in between these two, right? On state is allowed, off state is allowed. But in the case of microscopic world, what happens? You have on state as well as off state, the combination of these two. The linear combination of on and off is also an allowed state. So now the point is how you can store information in A and B. So A and B are complex numbers and they have to obey this condition. Mod A square plus mod B square equal to 1. And whatever choice you have, combination of A and B will satisfy this. All of them are your legitimate information. In the classical switch, you can store either on or off. In the microscopic world, if you have a switch, you have infinite number of combinations, infinite number of states possible, A and B, right? So this picture is called a block sphere, which is the three-dimensional representation of a qubit. So here you can see Ket0 state up on up state and Ket1 is the down state. Then the linear combinations are sitting along x-axis and the y-axis. The two angles are involved, theta and phi. So the theta and phi is nothing but your information, right? Classically, you have only on state or off state, only two information you can store. But here, if you look at theta and phi, you can store infinite combinations. Theta and phi can be taken in a different combinations. So it is, you in principle, at least theoretically, one can show that, one can understand that we can store infinite amount of information even in one single qubit, right? So this is nothing but quantum state or qubit, right? So this is the statement. This is the most important word, superposition, which you never seen it in the classical computation. We never seen superposition in the macroscopic world. Okay, so what is superposition? If on is one state, off is another state, the linear combination is also an allowed state. So what is the leverage we have? A and B are complex numbers satisfying this. Any choice of A and B are your valid state. All of them are valid state in which you can store the information. So the superposition is the ultimate aspect of quantum mechanics, which drives the power to quantum computation. So superposition is the significant one, right? The highest degree of superposition is called entanglement. So basically entanglement is a word derived from German, right? So in the language of German, entanglement means folded fingers, right? What do you mean by folded fingers? So if you have two hands and you can join the fingers like this, and you can easily take away. It's called the product. It's called product state. Right? Whatever you do, one hand will not affect the other hand. No influence at all. Right? On the other hand, when you have folded finger, entanglement means folded finger. So when you have a folded finger, when you do one side, something will happen on the other side, even if they are spatially separated. So when you have entangled the pair and one particle is here, the entangled particle, other particle is somewhere in Mars, let us say. If I do something here, something will happen to the other particle. How does it happen? Still, it's a very weird, very interesting. And if you ask me to explain, then I need to request the organizers to give one more session. Okay, so entanglement is completely weird aspect, but experimentally proved, and very philosophical aspects also involved. Right. Now, what is entanglement? Entanglement is nothing but highest degree of superposition. So superposition is nothing but this, the combination, linear combination of all allowed states, and highest degree of entanglement is nothing but highest degree of superposition is nothing but entanglement. Right. So to have an entanglement, you need at least two particles. So that's the reason why the subscripts are given 1 and 2. Particle, this is first particle, this is second particle. This is a mathematical symbol called a tensor product. Right. When you want to scale up one particle to 2, 2 to 3, 3 to 4 like that, then mathematically, how do you represent? You represent by means of an operation called tensor product. Why tensor product is used? Because tensor product preserve linear superposition. Superposition principle is respected when you do tensor product, not by any other mathematical formulation. Right. So this is the entanglement. And the opposite of for entanglement is a product state. It's called product state. So here you can see tensor product. So it is get psi1, 2 is a product state. If you are not able to write, if you cannot split the two particle system as a tensor product of single particle system, then it's called entangled state. So this is a very simple definition people always give. What is entanglement? Given a two particle system, if you can write down as a tensor product, it's called product state. If you cannot express two particle system as a tensor product, then it's called entangled state. So it is a definition for entanglement, mathematical definition for entanglement. Right. So this is one side. The other side is quantum operators, nothing but logic gates. Right. So in the classical computation, we also have a logic gates. Right. What are the logic gates? We know NOT gate, AND gate, OR gate, NAND, NOR, XOR. These are only few gates we know. But in the case of quantum computation, we have infinite number of gates. Why it is so? Because all the logic gates are unitary operators. All the logic gates are unitary operators. So because of unitary characteristics, unitarity characteristic, we have so many quantum logic gates. So unlike classical, quantum computation deals with a lot of quantum operators, right? So we always split the quantum operators into two types, single qubit and two qubit. Single qubit gates are well-known Pauli operators. People from physics background can understand this. So these are all called Pauli operator, nothing but spin operators. Pauli spin operators. And if you see this 0110, it is nothing but classically not operation. It's nothing but a not operation. So not operation is nothing but the on state becomes off state and off state becomes on state. That's the not operation. So typically Pauli X operator is nothing but a not operation. Right. The combination of all of them can be expressed in the most general form, which are nothing but a rotation. Which are nothing but the rotations. Right. So now this is an important slide. Here you can see the 2 qubit gates. Now I move to 2 qubit gates. So when you have 2 qubit gates, so SU means special unitary of dimension 4. It's a 4 by 4 matrix, and which can be written down as tensor product of single qubits, single qubit operator. So very simple definition. Let us make it very simple. So when you have a 2 qubit operator, you can write them as tensor product of single qubit operators. Then it's called local gates. It's called local gates. And note that local gates do not produce any entanglement, and hence it is of no interest. So we want to generate entanglement, right? For which local operations cannot work. On the other hand, there are 2 qubit operators which cannot be expressed as a tensor product of single qubit operators. 2 qubit operators cannot be expressed as a tensor product of single qubit operators. Those gates are called non-local gates, and non-local gates can produce entanglement. Note that non-local gates can produce entanglement, and we are interested in it. And when you start off the story of SU4 2 qubit operator, we thought that okay, I need to find out so-called universal quantum gate. Right. In the classical computation also we have universal gate, right? What is universal gate? NAND is a universal gate. Why you call it as a universal gate? Given a NAND, I can construct in different combinations. I can realize all other classical logics, right? That's why you call NAND or NOR as a universal gate. In a similar spirit, we try to find out universal quantum gate using which we try to construct all the 2 qubit operators. That was our intention, right? But the problem is half of them are local, half of them are non-local. We are interested only in the non-local gates. Why? Because non-local gates use entanglement. Right. The well-known example for non-local gate or 2 qubit gate is controlled not operation. This is the circuit symbol. The first line is called a control. The second line is called a target. So this is the input. These are the output. So understand, in the case of classical computation, you have something like 2 input and 1 output. But in the case of quantum operators, all the quantum gates, all the quantum operators are, let us say, 2 input, 2 output. And hence reversible is possible. Right. How does C0 work? Very simple. Whenever the first qubit is 0, it leaves the second qubit as such. Here you can see leftmost side is called first qubit or control qubit, and rightmost is the target qubit. So 0, 0 becomes 0, 0, 0, 1, 0, 1, 1, 0 becomes 1, 1. You can see the control becomes 1 and it flips the target. So 0 becomes 1. When 1, 1, you have 1, 0. So C0 is believed, and C0 indeed shown to be a universal quantum gate. So controlled not is a universal quantum gate, right? So whenever we study the quantum gates from the quantum circuit or synthesis point of view, we always have this circuit diagrams. C0, name of the gate, and circuit symbol, very important, and the matrix form, right? So matrix form will be very handy when you want to work out some of the calculation. Right. So if you ask me the question, sir, do we have only up to 2 qubit? No, the answer is no. But the point is 2 qubit gates are more than enough to study higher dimensional qubits. For example, if you have 5 qubit system, 6 qubit system, all those 6 qubit system can be operated by combination of single qubit and 2 qubit operators. So it is enough to study single qubit and 2 qubit operators in detail. So that is the reason why we restrict ourselves only to 2-qubit operators. So there are elementary gates that has been identified. So why we look for so-called quantum computer? So these are the main reasons. Okay, reversibility. So understand, quantum computers are reversible in nature. What do you mean by that? Right. Recall the truth table of OR gate. What is truth table of OR gate? 2 input and 1 output. What is the truth table? 0, 0, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 1. Right? So if you give you the output as 1, can you tell me the inputs? No, it's not possible. So you lost the information about your input. Right? Moment you go to the output, you lost your information about input. But in the case of quantum computer, it is not so. If you know the input, you can apply the unitary operator, you can find out the output. You can apply the inverse operation, you can come back to the initial state. So all the quantum operators, all the quantum logics are reversible in nature, which amounts to say that quantum computers are reversible computer, whereas classical computers are irreversible. Right. In fact, it has a lot of things to do with the thermodynamics. See, for example, you have a system, right? And you work for some time. And when you touch the CPU, you feel the heat, right? Why heat is coming out? Because you do all the process, right? And that comes out as a heat. So heat energy is emitted. The information is erased. Whenever you erase the information, whenever you delete a file from your system, it creates heat energy, right? And that goes in the form of heat energy. The erasing of information goes, right? But in the case of quantum computer, you will not erase any information, and all your information will be intact, and there won't be any heating effect. No temperature will be liberated because no information will be erased. Right. The another interesting fact is quantum superordinancy. People still debate on this. What is the quantum supremacy one can look for? Right. The third and most important thing from communication, quantum communication and cryptography point of view is nothing but no cloning theorem. So no cloning theorem tells you that you cannot copy an unknown state. You cannot copy an unknown state. So what do you mean by unknown state? Unless I make a measurement, I don't know what is the state of the quantum particle. If moment I make a measurement, what will happen? It will collapse to one of the allowed state. So this is the problem. So the unknown quantum state cannot be copied, and hence the intruder. So if someone is there in the line of attack between two communicants, he cannot copy the information. Unlike the classical information, we cannot copy. So it's called the no cloning theorem. So no cloning theorem indeed looked at in a very positive spirit, and it is power to the quantum computer. Right. So this is the last question in this segment. Can we realize quantum computer? And I take the help of Niels Bohr. Prediction is always difficult, especially if it is about future. Right. So moving to the last segment, I will quickly go through it so that we can have more time of the discussion. Right. So this is the last segment, introduction to quantum algorithm. Especially there are many people from so I just want to justify their presence and my talk as well. Right. Sir, can you see the screen, sir?
Yes, sir. Yes, sir.
Okay. Thank you. Thank you. Right. So moving further, so I want to show you the very simple example to show the power of quantum computer. Right. See, let us play a very simple game. It's called a classical penny flip game. And we have two participants, namely Alice and Bob. So we have a coin. Okay. It's a very fair coin. So I just showed you the one side, two sides of the coin. It's only one coin we are considering. And there is a person called the arbiter. He's a judge. Okay. So now the game is something like this. Bob will get a chance. He can keep the coin in the same state or he can flip it. When I say flip, head becomes tail or tail becomes head. Right. And he carry out this operation without the knowledge of Alice. Then Alice gets her turn. She can also do the same. Either she can keep in the same state, not knowing what is the state, and or she can ask the arbiter to flip the state. When I say flip, head becomes tail or tail becomes head. And Alice carries out without the knowledge of Bob. In the final turn, Bob makes the same strategy, either keeping it in the same state or flipping. And finally, the state of the coin is measured by the arbiter or the judge. So what is the rule of the game? If the same state of the coin, initial state and final state is the same, then Bob is declared as a winner. Otherwise, Alice is declared as a winner. Right? If you solve this problem classically, right, you can do this, of course, very easily one can do. We can see that the possibility for Alice and Bob to win in the game is 50-50. So both Alice and Bob can win the game 50-50%. Okay. Though it looks a very biased game, right? Alice gets only one chance, Bob gets two chances, but still winning possibility for Alice is 50% and winning percentage for Bob is also 50%. Right? When you play this game in quantum world, right? In the quantum world, everything remains the same. And instead of head and tail, we have so-called spin up and spin down, or 0 state and 1 state. Right? There is an operation called head-mod operation, which keeps the coin in the superposition state. Head-mod creates equal superposition. Right? Now, our friend Bob creates the equal superposition, and Alice is a classical player once again. So she can flip the coin or she can retain in the same state. Whatever she does, it will not affect the state of the coin because it's in the superposition, right? 0 plus 1 or 1 plus 0, one and the same, right? And in the final step, Hadamard gate is being applied by Bob, and Hadamard is the inverse of its own. So what will happen? 0 plus 1 becomes 0 or 1. Whatever be the initial state, that is brought back by the application of Hadamard operation. So Bob always wins the game irrespective of Alice move. So note that Bob is a quantum player. Bob is a quantum player who applies quantum strategy called Hadamard operation, whereas poor Alice is a classical player, right? But not knowing that Bob is a quantum player, Alice calls Bob many times. So now the point is all the time quantum player wins the game, right? This simple example shows the power of so-called quantum computation or quantum algorithm. In fact, this work was published in a very reputed physics journal called Physical Review Letters in the year 1999. The title of the paper is Quantum Strategies, given by David Mayer. Right. In fact, I would say this was the very first paper which talks about so-called quantum algorithm. Right. So as I said, there are two path-breaking works, Shor and Grover. So Grover's algorithm. Basically, Love Grover. He's an Indian. He studied in Meerut and he completed his PhD. Then he started working in Bell Laboratories in US, and he published this work, and that is called Grover's algorithm. Right? What is Grover's algorithm? Very simple. You take a telephone directory, assume that it has 100 names. 100 names are arranged in an alphabetical order. How to find out the phone number of a person? For example, Balakrishnan. Right? You want to find out the phone number of a Balakrishnan. What you do? You turn the page alphabetical order and you find out the name and phone number. On the other hand, if I give you the number, someone's number in the telephone directory, can you find out the name? The problem is it's not possible because it's called unsorted database. So in unsorted database, it's very difficult to find out the data. Right? Classically, how many atoms you need? Classically, you need n by 2. For example, 100 entry means 50 atoms you require on an average. See, if you are lucky on the day, very first attempt will give you the right answer. If you are unlucky on the day, you will get only 99th attempt, you will find the correct answer. So 1 plus 99 by 2, so 50. 50 is the average. On an average, 50 attempt is required to find the correct answer classically. But Love Grover proposed an algorithm, it's called Grover's algorithm, which help you to find out the correct answer in square root of n. For example, square root of 100 is 10. So classical computer takes 50 attempts, whereas quantum computer takes only 10 attempts. Now think of the data dealt by Google, which is several orders, right? When the number is very large, you see the power of Grover's algorithm, right? So what was the idea behind it? So it is a very simple oracle, right? So what it is, so I'm thinking of a number between 1 and 10. So I feed a number 78, oracle will tell no. If I feed a number 3, it will tell yes, right? So the classical computer, every time you have to check. Every time you have to feed and check, right? But in the quantum computer, what you do, you make all of them as a superposition, all possible, and you can find out the correct query. So here you can see no, and yes. And you can write your algorithm steps so that you can find out the correct answer in one single step. Right. This is the Grover search algorithm. I don't want to discuss in detail. And interesting to see that Love Grover published this paper once again in Physical Review Letters. And the title of the paper is very interesting. Quantum mechanics helps in searching for a needle in a haystack. I hope you can understand needle in a haystack. Finding a needle in a haystack is not so simple, but he gave a very interesting title. All right. So the next interesting aspect, which was path-breaking, namely Shor's factoring algorithm. So the current algorithm is called, RSA crypto system. What is a RSA crypto system? It is named after, named after three scientists, Reversed, Shamir, and Altman. So basically, it works on a concept of prime factorization. Right. So for example, I give you a number 15. What are the prime factors? 3 and 5. So 3 and 5 are nothing but the key. See, you know pretty well. There are two types of keys. One is public key, the other one is private key. For example, my email ID is sbalakrishnan@vat.ac.in. It is my username, which I give it to everyone. It's a public key. Right. There is another one. It's nothing but a password, which is a private key. So if I want to know what is the information I receive, I need to feed my public key, namely my username, and I should also feed my private key, namely password. So when I feed these two, then only I can read, right? So the RSA crypto system is believed to be so secure because finding factors of a huge number will take several years. When I say several years, indeed several years. Okay, factoring number even with a sophisticated supercomputer will take these many years. So practically, it is impossible to crack RSA crypto system. But what happened? Our friend Shor come up with a quantum algorithm which helps to factorize the number of the order of log n, in fact. Okay, so it is it shows the power, and the most secured crypto system, namely RSA crypto system, is under threat by the Shor's algorithm. So if you happen to develop quantum computer, you can feed Shor's algorithm and you can break RSA crypto system and you can steal all these important and secret files of many governments. Okay, that is the reason why quantum computer becomes so powerful. A lot of governments started funding for quantum computation. So the security of the country becomes under threat because of quantum computer. So we need to work on it, how to overcome that. Right. So if you ask me, the questions are how come all the quantum algorithms arrive its power? One is called quantum parallelism. So it's more than parallel computing. Okay, you can't really compare it to parallel computing. It's more than that. It comes through the concept of superposition. Here, the quantum algorithm exploits superposition and entanglement. So these two aspects are being exploited in the quantum algorithm, and which indeed shows the power. Right. So summary of algorithm, as you said, factorization and other unsorted database. There are other cryptographic protocols are also available. BB84, BB92. There are developed protocols are available from cryptographic point of view and communication point of view. But nevertheless, still a lot of things required. There are a lot of problems. It's called NP hard problem, non-polynomial hard problems. Okay, so non-polynomial hard problems should be solved effectively, right? So understand, we know the roadmap. Classical computer can solve, but it will take several centuries to solve it. We cannot imagine such a timeline. That is the reason why we look for an alternate machine which can help us to solve it in a least possible time with a high level of precision. Right. So this is the quantum algorithm. There's a lot of things to be done. Quantum algorithms. In fact, computer scientists need to do a lot in connection with physics. Okay. In the sense that all these features, if you want to write a quantum algorithm, you need to know basically little bit of quantum mechanics, not hardcore quantum mechanics. That is a little bit of quantum mechanics you need to know. And of course, physicists are aware of quantum mechanics at least at a very elementary level. And when computer scientists join hand with the physicists, they can come up with a path-breaking work in quantum algorithm. So there are a lot of scope there in the case of arriving at quantum algorithms. And you will not stop simply writing down algorithm. You will test it in some of the simulators, like IBM Qiskit and so on and so forth. So circuit synthesis is also very important. And the question of finding a universal quantum circuit or quantum logic gate still remains open. It's not yet solved. So these are all open areas. And from physics point of view, we look for a material which is an alternate to so-called silicon, right? So all our transistors are made up of silicon, right? What is an alternate for silicon when you have quantum computer, the hardware, right? So we always divide hardware and software. So hardware part is predominantly taken care by so-called physicists, electrical and electronics engineers, and the fundamental points are discussed by mathematicians, and the algorithm software side is predominantly taken care by computer scientists. So now we need to see how so-called machine learning and AI can be merged with quantum computation. That's what people are doing it. So now we are in a stage where we want to witness so-called classical computer merged with quantum mechanics. We have quantum computer. Now we want to merge quantum computer with AI and machine learning to see much more wonders. Right. So I come to the end of my talk. So these are the books I refer. I suggest the our audience to look into the second book, which is available, easy to read on. And Nielsen and Chong, it's a very celebrated book. It's a big book to read on, but it's an excellent book. People used to say it as a Bible for the subject. And so, of course, if you have any queries or any doubt or any help in the future to take up work in quantum computation, you're most welcome to approach me. Right. So this is the last slide. Thank you for your patient listening. And I always show this to my research scholars. Okay. So we should not never ever give up. A lot of bottlenecks in realizing quantum computer experimentally as well as theoretically, but it is very interesting. It's indeed very interesting. One should not give away the confidence and the patience. Right. So I stop here. I would like to thank you. And if you have questions, I would be very glad to answer. I hope I am on time. Anjanali sir, exactly 4:30.
Thank you, sir.
Yeah,
Thank
yeah,
you very much,
yeah.
sir.
I would like
Thank
to
you
take
very much.
questions if there are questions.
It is now time for the questions and answer section. The participants are open to ask the questions directly the resource person, as Palkrishna sir, or you can also put the questions in the chat box.
I think Sunita ma'am has a question as she has raised her hand. Sir, I think Sunita ma'am has raised her hand. I think you have to unmute her.
Okay.
Okay.
Sir, Sunita.
Samsura sir, please unmute the
Sir,
Sunita madam.
we are giving mic, sir. Sunita.
Yeah, moment they raise the hand.
Sunita Valluri.
Yeah.
Yeah.
Garigapata. Okay, one minute, sir. 1 minute. Sunita. Complete pair button. Sunita.
SUNI.
SU.
NITHA.
Sunita. Okay, one minute, sir. Hello, Mike. Okay, madam, you can ask, madam. Sunita, madam.
Sunita madam, please ask the question, madam.
Good afternoon, sir.
Good afternoon.
Sir, actually, I wish that we would get an opportunity to unmute ourselves right from the beginning, because we are going to get some doubts in between the lecture. So that's why I have raised the hand.
Okay.
And of course, I have a doubt, sir.
Please.
So how would you we visualize that it is going to happen a rigorous one within a short period of span? Can we expect that short period of span would be?
You mean for the realization of
Quantum
computation?
computation. Yes,
Okay. Right. True. See, a lot of efforts have been taken across the globe, right? Many countries have given a lot of funding. Even government of India has initiated national quantum mission with a amount of 6,000 crores in 8 years, with an intention to realize 1,000 qubit computer, right? But the point is that we require a lot of manpower. Many people need to be there to work on. And as I keep on pointing out, the subject as such is multidisciplinary. We need to have a contribution from every sphere, right? Namely computer scientists, electrical, electronics engineer, physicists, mathematicians, and so on and so forth. So considering that fact, we need to train a lot of people. And India is a country where we find a lot of people, and we need to train so that we can take an advantage of our human resource. Yes, it is possible, ma'am. The way we go, definitely we will achieve.
Thank you, sir. It's our pleasure.
Yes, thank you. Yes, Sriram.
Sir, Sriram.
Yeah.
Sir, unmute Sriram.
Okay, sir. N. Sriram. N. Sriram.
Yes.
N. Sriram. SRE, sir. SRE. Yes, N. Sriram. Captain. Dot. N. Dot. N. Sriram. Okay, sir. Sriram, sir, please raise your question, sir. Hello, Sriram, sir. Is it audible?
Sriram, sir, please ask the question.
Hello, Sriram, sir. Are you hearing, sir? Sriram, sir?
No, I think.
Okay.
Yeah.
Sir, I have one small question, sir. Myself.
Yeah, please.
Sir, the spin state of the photon is highly unstable, sir. Is it?
Sorry.
But which is the most stable? I mean, which is most difficult task, sir? Whether stabilizing the spin state of photon or designing a quantum circuit, sir? Circuit synthesis.
See.
Which is most difficult task?
Right, I understand. See, the point is, what is your physical system? See, every system has its own advantage and disadvantage. See, for example, when you take electron spin can be used. Okay, electron, by applying a magnetic field, I can orient the spin either up or down. Okay, very simple. Up is on state, down is off state. Ket 0, Ket 1 can be created. Very simple. But the problem is, electron is a negatively charged particle which interacts with the environment. So it will decohere from its position. It's called decoherence. Okay. So realizing entanglement or physical system or in a controlled way using electron is very difficult when compared to photon. Okay. But having a single source photon is very difficult. If I have a single photon, I can realize.
Okay.
Right, but realizing single photon itself is a task. Right?
Yeah. Okay.
So that's the reason why we struggled, right? Why people could not, take it up because of this fact only.
Yeah. Thank you, sir.
Yeah.
Sriram, sir, are you there? Sriram, sir?
No, I think Shankar Narayan sir is here to have a question. Sir, can you unmute for Shankar Narayan sir and
Sir, Samsara, sir?
Yes, sir. Yes, sir.
Yes,
Please
sir.
unmute Shankar Narayan, sir.
Okay, okay, sir.
Shankar, yes, Shankar. Sir.
Yes.
Sir, Shankar Narayan.
Shankar Narayan, sir, please ask.
Sir, Shankar Narayan, sir. Hello, sir. First of all,
Okay, PNB Kishore, sir. Sir, can you unmute? There is one more.
PNB Kishore.
Correct.
PNB Kishore.
Yes. Yeah. Kishore, sir, do you have any question?
Option. Hello, sir. PNB Kishore, sir. Are you hearing, sir? Hello, sir.
Sir,
Just a communication problem, sir. Once you check. Voice is not audible, sir.
Shankar Narayan, sir, do you have a question? You can unmute and. Okay,
Hello,
fine,
sir.
I think.
sir, excuse me, sir.
Yes, ma'am.
Can you please elaborate on entanglement, sir?
Okay, right. So
Anything can be entangled or coming to living organisms as an example, so that we can easily understood some more content.
okay, see, that's what, see, when microscopic world only exhibit the concept of superposition. Okay, microscopic world, when I say so-called, proton, electron, photon, all this, particles, subatomic particle, they have a tendency to exhibit superposition when they are more in number. And the in a very, very superficial way, I can state that the entanglement is the highest degree of superposition. Right. So we have an interaction, the so-called, the physical interaction between the two particles create such a state which is known as entangled state. And people have proved that, and it's called entanglement swapping. So, for example, you take three particles, A, B, C. A is entangled with B, A is entangled with C also. You do some operation between AB and AC, thereby you can create an entanglement between B and C. So the particle which never interacted before can also be created entanglement. Okay. So this is the characteristic of a microscopic world. The macroscopic world, we never realize all those aspects at all. Okay. But there are few cases which are not yet well established. Okay. It's called sensory organs of migratory birds. Right, we know migratory birds which travel from one continent to another continent. In fact, interestingly, they travel 15 to 20 hours across the ocean without any break. Without any break, they travel, right? They come all the way from USA to Vedantangal, right? And how do they travel? How their GPS works? Because of the concept of entanglement in their eyes. Okay, so all the migratory birds have a pigment which is entangled, and it has a sensory which can measure so-called Earth magnetic field. So Earth magnetic field very sensible, and it can be measured by the entangled pigment what those migratory birds have. So using those entangled pigment, they manage to travel across the ocean without any deviation, come here, stay here for 3 to 4 months, and go back to their home without any deviation. So in the migratory birds, people are talking about it, and this is called quantum sensing. Right? Sensing of magnetic field is not so simple. And if you have a quantum sensing mission or instrument, then our GPS system will be so precise. GPS, now also GPS is fine, but still it's a satellite. And there are other issues are there, climatic condition, and there are other political reasons also there to cut off. Okay, so the GPS will be well established if you have a very high level of quantum sensing instrument. So that's the reason why quantum sensors or quantum sensing is very important domain in the National Quantum Mission as well. So this is one example I can tell you. Okay, where the entanglement come into picture. The other aspect is something like our the so-called the taste bud. Human has a taste bud, right? How it works. People also talk about entanglement in a different sense. But it's not a quantum state. They also use the notion of entanglement and all. So these are all some of the cases where we have a very large picture at a macroscopic level. Yes, we do have cases. Yeah, we do have examples for entanglement at a macroscopic level.
The third day session is also about the entanglement, sir. We will.
Yes, exactly. Yeah.
More about
he can.
Yeah.
Specifically.
It's all about entanglement and applications.
Yeah. My intention was very simple. I want to narrate the stories. I don't want to trouble the participants by writing equations and all.
No problem, sir. Thank you, sir. Thank you very much for a wonderful session you have given. Evolution of the quantum computing through the fundamentals, particularly starting with Einstein photoelectric equation, photonics, and quantum mechanics, Moore's law, superposition. Lots of almost all the fundamentals you have covered in this lecture, sir. Thank you very much for your lecture, and also explain the questions in very detailed way. Thank you very much, sir. Thank you very much for taking this section. Thank you very much, sir.
Thank you.
Okay, so now I invite Dr. SLV Mallikarjun, sir. Sir, please propose the formal vote of thanks to our resource person and management and every participants who are in the car. So, who made this event a success? Welcome, Mallikarjun, sir. Please take the session.
Hello, sir. Hello, sir. 1 minute. We asked Shankar Narayanan, sir. Sir gave me a message personally.
Okay, sir. Okay. Please.
Sir, is it audible, sir? Shankar Narayanan, sir? Hello, sir?
Sir, you are audible, but sir has to unmute and speak, and seems some problem at his end.
Sir, sir, send me message. I am unable to unmute, sir. But we have given mic and video, sir. Sir, Shankar Narayanan, sir. Once please leave and once again you rejoin, sir. Please pause. Sir has left, sir.
Yeah.
Again, sir will join, sir. Rejoin, sir.
I hope the session is not boring.
Session is very good, sir.
No, sir, it is very interesting, sir.
Very interesting, sir. Fundamentals of physics and quantum computing. Very good, sir.
Very much interesting, sir. From the ground level, you have bring up everything, sir. Thank you. Such a nice session we have.
Samsara, sir?
Sir, I am searching for Shankar Narayanan.
Make a phone call to Shankar Narayanan, sir, to rejoin the session, please.
I gave. Sir, personally, I am calling, sir.
Okay.
Sir, Shankarnarayan, sir. Hello, sir. Sir, I allow mic and camera also to you, sir. But what is okay, sir. Okay.
Join.
At the time of joining, those are, sir.
Okay, sir. That is your side problem, sir. Okay.
Can you ask question?
Okay. Can you ask the question to Samsara, sir?
Sir, you can ask, sir. Here. Hello. Sir. Can you hear me? Hello, sir.
Audible, sir.
Is it audible, sir? Second answer voices. Sir, please ask, sir.
Voice is low but audible.
Can you hear me?
Yes, sir. Yes, sir.
Yes, sir.
Balkrishnan, sir.
Yes.
Sir, voice is it audible, sir?
Yeah.
Phone.
Yeah, okay. So I have one question. So we have been thinking about various physical systems to realize the qubit, right?
Correct.
So one possible promising candidate in the recent years is the superconducting qubit.
Correct.
Yeah. So how do we realize the qubits in the superconducting system?
Okay, so in the case of superconducting qubits, we have Cooper pair using which we can realize. But once again, the problem is we need to have a lot of coolant. We need a liquid nitrogen.
Oh, yeah, I understand the difficulty behind that because it's all at the low temperature.
Correct.
Yeah, the point is, here you have, the electrons are supposed to be paired and they travel, kind of thing, right?
Right.
And they go together with, some exotic attraction between them.
Yeah.
Right? And
yes.
In such scenario, how do we actually realize the qubit two-level system?
Two-level system, it comes from the different level it occupies. The pair, the Cooper pair, they occupies at a different levels, energy levels. So we give the name. So if they occupy one energy level, we mark it as Ket 0. The another energy level, we mark it as Ket 1. So the transit.
What I understand is when the electrons they travel together, they are no longer like a fermion carrying spin arm.
Right. True.
Yeah. So they go together. They can be treated as a boson, right?
Correct.
So it's some kind of condensation kind of thing, right?
Right. Exactly. True.
Now, in such scenario, when people talk about this, the realization of qubits through Josephson current and things like that. So can you throw some light if possible, or do we have to discuss separately?
No, I think it will take a long discussion. I need to draw some diagram.
Okay.
Yeah.
So I'm just what people say is that through Josephson junction, it seems a more practical way of realizing the qubit. So
right.
Because Josephson junction is basically a current between superconductors separated by a material in between, right?
Correct.
Material or dielectric in between. So when you take current, thousands of electrons might be going from one side or that side.
Right.
So in such scenario, how do we? I am unable to comprehend how the idea of qubits come into play. Yeah.
Right. So there also we try to reduce the number. See, there are two aspects. One is the physical qubit. The other one is logical qubit. So the physical qubits is what they are talking about. When they say, 1,000 qubits, they realize that people say, Google and IBM, right? So there are two aspects they are talking about. One is the physical qubit, the other one is logical qubits. So using physical qubits, how many logical qubits can be used?
Okay. Okay. So anyway, because it seems to be having a more promising physical system than all the physical systems which people have been tried out earlier, right?
Correct.
And I presume these IBM computers and all, they have been working with the superconducting system, right?
Right. True.
So,
That's why we have seen that big picture, right? Keeping a coolant and all. That is a very celebrated picture that's being shared. No?
right, yeah.
A superconducting.
Yeah, correct, yeah. So one needs to understand more closely from the computer matter point of view how one actually realizes the qubit and how it is connected to, because Joseph's induction current is something which can be physically measured. So that is the beauty of the superconducting system.
Correct.
And now they say that Joseph's induction current can be directly related to the qubit kind of transition.
Right.
And there are words which say that one can actually control this Josephson current by external magnetic field and stuff like that.
Right.
So one needs to study more on that. I think there are some recent studies going on where people try to understand and control the Josephson junction with the external magnetic field.
Right. True. There also we require very high magnetic field.
More detail on that. Yeah. Okay. Okay, thank you.
Yeah. Thank you, sir. Thank you. Yeah.
Thank you, sir.
Thank you, sir. Thank you very much.
Thank you.
Okay, sir. Thank you. Thank you very much.
Thank you, sir. Thank you for your session. And now I invite Dr. S.W. Mallikarjun, sir, to propose the formal vote of thanks. Mallikarjun, sir, welcome, sir.
Yes, sir.
Okay. Carry on, sir.
So, good evening, sir.
Okay, sir. Oh, carry on. You are audible.
Okay. Good evening, sir. I'm S.W. Mallikarjun from Department of Physics, Bapatla Engineering College, Bapatla. Sir, on behalf of the Department of Physics and participants, I would like to express my heartfelt thanks to our today's resource person. We sincerely thanks to Balakrishnan, sir, who delivered such an excellent, highly informative presentation on foundations of quantum computation, starting from very bottom level and interconnecting the physics and the computation ideas. So despite of this busy schedule, he graciously accepted our invitation and shared his valuable knowledge with us. Actually, we are very fortunate to have such type of lecture from you, sir. Really, we feel very happy because we the physics persons and you made me interconnect the physics and the computers. Definitely, this is going to show a good impact and more interest towards raising this. I would like to express my sincere gratitude to our principal, Dr. B. Srinivasa Rao, sir, our HOD madam, Dr. B. Aruna madam, all other participants and staff members for their active involvement in cooperation in making today's session a great success. Thank you, one and all, sir.
Sir, Anjay, sir. Anjay,
Okay,
sir.
thank you, Mallikarjun, sir. So the participants can fill the feedback form, which is going to share in the chat box and WhatsApp group also. The participants are requested to join tomorrow's session at least 15 minutes before the scheduled time. This will ensure us for the smooth conduct of the program. So, Mallikarjun, sir, please share the feedback form to me.
Sir, already
First, I
shared,
will.
sir. Yesterday, Shah also shared you.
Once again, so it's
Once again, it should be
link. I don't know what's the opinion.
Sir, one small request from us, sir, from our side. Please share the PPT with us also, sir. Thank you, sir.
madam.
Thank you very much.
మేడం దీనిలో మీది వాట్సాప్ ఉంది కదా డిస్కౌంట్ చేస్తాను సారీ ఫ్రెండ్స్ ఫీడ్బ్యాక్ లింక్ పెడతాం అదే పెట్టారు గవర్నమెంట్ ముందు పెట్టేయాల్సింది ఇప్పుడు
Okay, sir. So thanks a lot. Thanks to everyone. Arna ma'am.
Thank you very much, sir.
Thank you.
Thank you very
ma'am.
much, sir.
Thank you.
Thank you very much.
Anjaneli sir, thank you. Thanks a lot.
Thank you very much, sir.
Right,
Thank you.
right. Yeah. Thank you.
Thank you, sir. Thank you.
Have a good day, sir.
Right. Thanks a lot, ma'am. Thank you.
Thank you.
Sir, all dear participants, feedback link is posted in WhatsApp group, sir. Please fill it and submit it, sir. Sir, feedback link is active, sir. For 1 hour, it will be closed, sir. After 1 hour, all of you fill and submit it, sir. Thank you, sir.
So thank you all the participants. Now the session is going to close. All the participants are requested to join tomorrow's session at least 15 minutes before.